Okay, so let us talk of trees. What are they? We will understand what are trees, what are binary trees. Trees can be anything. You can have n-ary trees, n children, ternary trees, 3 children. But most often you have binary trees, 2 children at each node. 2 means maximum 2 children. Binary search tree, the kind of traversals we can do, and different things we will see. So when do we use trees? Whenever you have hierarchical data, you use trees. For example, in a book, you have chapters. Chapters have subsections. Chapters have sections. Sections have subsections. So there is a hierarchy. Every node you can have n children. A book can have n chapters. A chapter can have n sections. A section can have n subsections. So that will be a n-ary tree. Whenever you have a hierarchy, then you get to tree. If you are seeing the file system, you are seeing a hierarchy. If you are seeing a table of content of a book, it's a hierarchy. Maybe you are talking of countries and states and cities, and things are contained within them. So states are contained within country, and cities are contained within states. So wherever you have a hierarchy, you can imagine trees. It could be a binary, it could be more. So for example, this tree is a ternary tree. If you see the maximum degree, when we say degree, what is that degree? Degree is basically the number of children at a place. So the degree of this node is 3, the degree of this node is 1, the degree of this node is 1, like that. So the maximum degree of this tree is basically 3, so we can call it a ternary tree as of now. Okay, so that's fine. Okay, so we have nodes. These are nodes, right? So let me, sorry, basically these are nodes, A, B, C, D. These are nodes, and you have edges, right? You have edges, and you have a parent-child relationship. B, C, and D are children of A. A is parent of B, C, D. Even when we say parent and child, you can also extend it to ancestor and descendant. For example, if I say who are the descendants of B, E and I are descendants of B. Who are the descendants of C? F and G are descendants. So basically the entire family tree, if you like to call it, the entire family tree beyond that single node is the descendants. And ascendants basically means that who are the parent, grandparent, and grandparent. So the ascendants of I will be E, B, and A. So there are certain terminologies. We will possibly see it as we go. And how do you know you want to use tree? One is that the data may be hierarchical. Uh, the other thing is basically you can think how much order complexity you want. Okay, what is your goal? If you are happy with order n, if order n is good enough with you, you can be happy with linked list, no problem. You can have a simple linked list, very simple, good. If you are happy with order log n, okay, we will understand that a binary search tree, if it is balanced means it's not skewed to the one side, it is balanced. All the nodes are like in a balanced way added. So we will see the height or depth, as we call, of that tree is log n. So that is why the search complexity or insert complexity or delete complexity in a tree is order log n, provided it is balanced. If it is skewed, if the tree is skewed heavily towards the one side, all the children are towards the left, then the tree degenerates to a linked list with only the left pointer being filled, and the order complexity degenerates to order n. So it depends how much search complexity do you want. Tree is order log n. If log n is also too costly for you, then you can go for hash tables. You can have a hash table, and given any key, you directly apply a hash function, get the index, and possibly at that bucket you will have only one node and you get order 1. So basically one way to decide which data structure to use is what is the cost you are willing to spend. If you have a lot of CPU power and n is not very large, order n is good enough, linked list is okay. If log n tree, if order 1 you want a very quick search, then hash table. So like that you can choose. Anyway, so we proceed. So even an organization hierarchy can literally be represented as a tree. If this is your company and you have people, president, vice president, all that, you can think of it as a tree also. A book TOC I already talked. A book has n chapters. So normally a binary tree will not suffice here. If you are talking of a book TOC, you are talking of a n-ary tree. How do you implement a n-ary tree? Binary tree are simple: left pointer, right pointer. How do I have n pointers? You can have an array of pointers. So you can have something like node t star, arr, and max children, something like that. Array of, so you are saying totally max children pointers, array of pointers where maximum number of nodes is max children. So you can have that. Expression trees, that's very interesting. In fact, you would have seen those infix, postfix, prefix kind of expressions. So they can be represented as a tree, and it's very interesting. They are all represented as one tree. If you traverse in order manner, you get infix expression. If you traverse in prefix, pre-order traversal, you get prefix and postfix. Similarly, post order, we will see what this in order, pre-order, post order are, but expression trees is another example. Search trees, that is I think the most commonly seen. It's a binary search tree where you keep things order. You keep something at every node, and the rule is that everything on the left subtree, right, this is the left subtree, on my left child, the entire tree rooted at the left child is left subtree. So the rule is that everything in the left subtree is lesser than the current root node. Everything in the right subtree, this is the right subtree, is greater than the current root node. So that's binary search tree, and balanced binary search tree is what leads to order log n complexity. A skewed binary search tree will lead to order n complexity, right? So our goal most often is balanced binary search tree. These are some terms we have seen. We know what a node is, edge, root is the root, parent, child, all this we know. Siblings is like the kind of the brother and sister. Path, you can consider path to be like if you are tracing the path from this node till this. Sometimes that may be needed, sometimes, but mostly it's not really much needed. So that's okay. Subtree we understand. We often talk in this term that a node and a left subtree and a right subtree. We often talk in that terms. We often think in that terms. You often can code in that term because you can write a recursive function. You can say that you want to process this tree. Maybe you are doing in order traversal. Okay, the way to process this is process this. Mind it is in order. So process the left, then process this node, then process the right subtree. So, and how do I process the right subtree? Using the same function recursively. So trees are recursive, and you can exploit that recursiveness in writing very easy recursive functions. Should you write recursive functions? If you are sure that the stack will not overflow and things will be well, you can write recursive functions. But if the trees have tens of thousands or millions of nodes, recursion can prove very costly. Sometimes you can convert all recursive function to iterative, some even without a stack. But one mechanical way of converting all recursive to iterative is that you maintain the stack yourself. You don't depend on the compiler that the function call stack is automatically maintained. You maintain the stack of useful information yourself. So you can judge whether recursive or iterative is good for you. Recursive is certainly easier. Iterative is almost always more efficient. Okay, so that's okay. Degree of a node we know, number of children. Leaf nodes, they are the leaf. they are the leaf. So a leaf doesn't have any branches, a leaf doesn't have any children. They are like the terminal nodes. So they have zero children. For them, the left and right both pointers are null. A level of a node, there is a notion of level. You can say it is level 0, it is level 1, it is level 2. So you can kind of give a level. In fact, when we talk of traversals, in addition to pre-order, post-order and in-order, there is a level order traversal also, that you first go to this node, then this node, then this node, then this, then this, then this, like that. So there is a concept of level, and of course there is a concept of height or depth. Height and depth both are the same. So this tree has depth 2 because the length of the path from the root till the leaf is 2, maximum length, right? Maximum length. If I add another one more node, the depth will become 3 because the longest path towards the leaf is 3. Depth or height, one and the same, and depth is what my order complexity is. If I am balanced and I don't go very deep, I go wide, then my order complexity is log n. If I am skewed and I am going deep, 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 I go to depth n because every node is like on the left. So then it's order n. So depth and height are two important things. Complete full tree, let's understand. So complete full tree basically means something like this, that it's kind of a complete tree, right? It's fully filled, or even if it is not fully filled, it is filled in that order. So next it should be this child and so on. So this is more or less, at least on the direction of a complete tree. It is a complete tree, although may not be full tree, but this is not a complete tree and full tree, because this is like, so complete and full are kind of indicating how balanced we are, right? So anyway, we are not intent is not to master all the vocabulary at once. As we go, we will see. So this children, some examples are given. BCD are children, C is parent of FG, that's okay. EBA are ancestor of I. So if I say I, who are the parent, grandparent, like ancestors, so these are the ancestors. If I say descendants of B, E and I are descendants. So like that you can say siblings are children of the same parent, F and G, but G and H are not siblings because they are children of different parents. That's okay. Nodes, edges, path, we understand that, and the length of the longest path from root to the farthest leaf is basically the depth. If we say maxima of this, that gives the depth. So degree is okay, and degree is basically what determines am I a binary tree. If maximum degree is 2, then I am a binary tree. If maximum degree is 3, I am a ternary tree. Leaf nodes don't have any children, that's fine. So sometimes these are called leaf nodes, and sometimes other nodes are called internal nodes who have at least one child. They are called internal nodes sometimes. That's okay. So every node in the tree has one parent, at exactly one parent. Only one node doesn't have a parent, which is the absolute root. He doesn't have a parent. That's okay. So level order traversal. Now vocabulary may differ. For example, I just said level 0, level 1, level 2. So different algorithms may have different conventions, whether I call it level 0 or level 1. So that's up to each person. So tree is naturally recursive. So what the definition we have is, a tree is a root node. In fact the proper definition would be, a tree is either null, you can have an empty tree, or it is a node having n subtrees. Okay, n subtrees. So that is the formal definition of a n-ary tree, that it is either null, it has no node, or it has one node having n subtrees. So that's the formal definition. That's okay. This is like okay. All this is we have understood. So normally, what is the maximum number of nodes at level k? The important thing to understand is that it is 2 raised to power n or n minus 2 raised to power l or l minus 1, where l is the level. So for example, if I consider, let me draw here only. Yeah, let me draw here. So let's say at this level I have one node, at this level I have two nodes, and in the next level I have four nodes. So you can understand that every level I get twice the previous count, right? So 1 into 2, 2 into 4, because you can understand very well at this level, if I have x nodes, at the next level them of every one of them has two children, so twice x, right? So if I go k level deep, then my number of nodes is roughly 2 raised to k. Of course it depends on how I am counting, it's level 1 or level 0, like that. So it may be 2 raised to a k or 2 raised to a k minus 1, but you can understand that the numbers grow like this. And if you consider mathematics, 1 plus 2 plus 4, that means 2 raised to a 2 plus 2 raised to a 3 plus 2 raised to a n, if you do, that comes to be 2 raised to a n plus 1, possibly minus 1. So you can, yeah, that's what it is. So basically, if we see the total number of nodes in the tree also, that is just kind of one more multiplication with 2 roughly. So this is a simple geometric progression, or even you can understand them as, if you consider them bits, so this one is this bit, this 2 is this bit, and this 4 is this bit. So it is basically all ones, n ones, and that would be 2 raised to our n plus 1 minus 1. These maths can help you a little, just to prove in your own mind that log n thing, that's all. So all we care is that the depth is log n, and the number of nodes at level x is roughly 2 raised to our x, maybe plus 2 raised to our x plus 1 or 2 raised to our x minus 1. So that's okay. I think we are not going much there. So this is just a precursor kind of thing. We will get to the code. Basically the important thing is the code. Okay, so we will understand the code. This is just a some kind of theory.